Apologies to our viewers online. There's a sunny strip across the board. Those present in the actual lecture have a better screen in front of them. Yeah. Okay, we did this, and we still need to prove it. We haven't done. So what it says is, okay, so what does it say? So we have an action, group G, acting on a set. You want to count all the orbits of that action. And this theorem tells you that when you look at all the elements of the group and count how many fixed points they have each, and look at the average number of fixed points, that is giving you the number of orbits. I've got two screens, one is worse than the other. There's just that one. That one's got a bit of some in there. But, yeah. Okay. We're piecing together the proof of the orbit counting lemma, which says that the number of orbits is equal to the average number of fixed points. And what we'll use is this, what was the Lemma 1418, which says that when you look at two elements of the set X that's being acted upon, which are in the same orbit, then the stabilizers are isomorphic. So we'll only use, in fact, for the proof, we only need that their stabilizers have the same size. Okay. But we proved that they're isomorphic because that's the way. Well, because it's not much harder to prove that it's actually there's a bijection which preserves the group structure, then just prove that it's a bijection. Okay, and the second thing, what do we need? Theorem 1411. I forgot the book. Oh yeah. And the second thing we need is this theorem 1411, which is that the size of an orbit is equal to the index of the stabilizer. Or in other words, the size of the group is equal to the size of the order of the group is equal to the order of the stabilizer times the size of the orbit. Okay, so these are the ingredients that we have, and the way it's done, the best way you can do it, is you look at a bipartite graph. Is that the thing? Sorry. I'm not repeating it for the first time. Okay, you'll be all right. So all we're doing is proving the orbit counting lemma. Oh, yeah. Now, okay, so I'm creating a graph, okay? It has two parts. So on one side, I put all the elements of the group G, G1, so on. These are the vertices, okay, or nodes. And on the other side, I put all the x's. Okay. Now, what I'm going to do is put an edge between G and X. So Gx is an edge. Oh, it's not showing. If Gx is x. Okay. So if G sends x to itself, then then I'll put an edge. Okay. So now, how many edges are there? So how many edges are there coming out of G1? You know that's not the answer. That one. So the same answer is, so the same question really asks, how many x's does G fix? Okay. So how many x's are not moved by this particular element?
The center?
No.
The set of x minus.
So the question is, how many fixed points does G have? I'm looking. So G is connected to x if and only if G moves x to x. So it doesn't move it. Okay. So to how many points is it connected? Well, it's connected to as many points as it fixes. So what it's connected to is the fixed point set of this G1. Okay. Do you agree? You have to agree, otherwise. Okay. So the number of edges coming out of G1 is the size of the fixed point set. Okay. So the total number of edges that I get is, well, I look at all the G's and add it all together. Okay. Do you agree? So now, that doesn't help much, does it? But how many edges are coming out of X4? How many edges are coming out of X4? 3. But why? So what is it called that is the set of all elements in G that don't move X anywhere? Yes.
No, there's too many definitions in this chapter. They're all called differently.
Yes, but they are.
G's that don't move X, centralized. Oh, X.
That's only in the conjugation action. But you said it right the first time round. It's the stabilizer of X. Stabilizer.
Singular.
The set is called the stabilizer.
Oh, the stabilizer set.
Ah.
It actually turns out to be a subgroup. So the subgroup is called the stabilizer. It's probably at the very beginning of the chapter, something like that.
Why do they all have different names?
Because if they all had the same name, you wouldn't know what you're talking about.
It's not like
Okay.
the word Smurf.
So this is the GX4.
John Bonson, he gives different names to the same thing.
These are different things. GX4. Okay. So the number of edges going out of X4 is the order of the stabilizer. Okay. So the number of edges in total is, you add all the orders of the stabilizers. Okay. Now they have to be the same because it's the same number of the same edges. So that's a quite a common trick in combinatorics, where you look at one thing and do two different ways of counting it, and they have to be the same, and they give you something interesting. But now we still have a little bit of work to do. So from here, what we're going to do is, well, this is the set X. So, and we know the set X is split into orbits. So this is the orbit of X, this is the orbit of Z, and so on. And this is called OX, the orbit of X. Okay? We know that, I hope. So what we're trying to do here is we're adding the size of the stabilizer over all these X's. What I've just shown some time ago. Oh, it's at the top of this sheet. So excuse me for moving for a second. Is that if you have two X's in the same orbit, then their stabilizers are isomorphic. In particular, they have the same order. So what we're going to do here is add it over all the orbits. OX is an orbit. And we're going to add the order of GY over all the elements of this orbit. Okay. So now this is, what are we doing? Well, OX is that stays. But now we know that these GYs for the elements of the same orbit, they're all the same. Okay, so can rewrite it like this. Adding the same number O sub X size of times, so I get O sub X size of times that number. Okay. Is there one? Put a third screen there. Tomorrow we have 3, 4. Okay, so this is that. Now, what is this?
Can't keep that still. She's in Sheffield, it's really unhelpful.
Now we need to recall this theorem 1411. And that's the size of an orbit is the index of G, the index of the stabilizer in G. So OX times GX is nothing else than
So the GX.
G.
Yeah.
Yes. Okay. So now we're adding G
What? Where did
and
you
G
call? Where
and
did,
G
sorry,
and G and G and G.
where did you call that from then?
Theorem 1411. Okay, so we're adding G how many times to itself? The number of orbits. Once for every orbit, right? And we said in the assumption of the theorem that the number of orbit is K. So this is K times the order of the group G. And now I think I should bring back the theorem 1419. It's starting to be a long chapter. Oh, the orbit count. Look at this. So this is what we're trying to prove. K is the number of orbits. And this is promising that K is 1 over the order of G times the sum. And this is saying this sum is K times the order of the group. So divide that equality by the order of the group G, you get exactly this. So because I'm running out of paper. Okay, any questions?
Oh, then why did you not bring more paper?
Oh, I've got some.
Oh god,
It's still on out there. There's one for a whole one line.
doing
Don't start doing it. My housemates all do it.
it. Do they keep saying it?
Yeah.
I love it.
Because they're all Star Wars.
And Game Grumps fans.
No, just
Oh, right.
Paper 10. Any questions before we move on? No? So the proof is quite a simple double counting argument. Count the edges on the left, count the edges on the right. It has to be the same number. Example. What do I call it? 1420. So it's a silly example. G is 1, 1, 3. 1, 3, 2, 5.
Yeah.
it's like on the brain. Must be the screen. Must be the screen. Must be the screen.
And 2, 5. That's a subgroup.
Have you seriously put the word silly?
Yeah.
Oh wow.
Actually, what? It is a silly.
Oh, wow.
I'm going to write this down. It's silly.
No, that was silly exam.
Example.
Example silly. Call for an equation silly.
Is that am I the first person to write silly in the lecture? Probably not.
No, but you're the first person to give 2 IOUs out to students where they can write that in their exam. Jan promises that this theorem is correct. And I will write it in the exam.
Okay.
I hope mine gets marked right. Jan promise.
That's the light.
How many fixed points?
Yeah, because if it got moderated.
Okay. So the identity. So the identity. Does it move anything? No.
Mm-hmm.
So how many fixed points? So it has 5 fixed points.
Yeah,
1, 2, 3, 4, 5. 1, 3. That moves 1 and 3, but leaves 2, 4, and 5 in place. So it has 3 fixed points. 1, 3, 2, 5. That only leaves 4 in place, right? And this one moves 2 and 5, but leaves. So the average number of fixed points is 12 divided by 4. It's 3. Okay.
So because the numbers that are moving, you can't be other numbers. Yeah, that's what I mean. So like the first set, 1 and 3, it's 2, 4, and 5 that are moving. They're not moving. Sorry.
So if you have it's a permutation that sends 1 to 3, 3 to 1, 2 to 2, 4 to 4, and 5 to 5. Permutation in cycle notation.
Where did you get 12 from? 5, 3, and 1. 5,
5,
3,
3
and 1,
plus
and 3.
5 plus 3 plus 1 plus 3.
Got you.
Okay. Are we all there?
And it's because
Now?
we divided it by 4 because that's how many is in that set. So, just breaking it completely down.
Now, what are the orbits? Okay, so 1 can move to 3, and only 3, if it doesn't stay put. So that's one orbit. 2 can move to 5, and nowhere else. And 4 is never moved anywhere. 3 orbits. 3 orbits. Okay.
What's the second?
Hmm?
What's the second? That's perfect.
No, but we have a proof. This is an example to demonstrate how it is.
I just feel like we knew it worked already.
Okay.
I didn't think it sounds surprised, like that proof up and it's not real. It works, what? I'm putting not quite as silly.
It's coloring the vertices of the square.
Colouring the vertices of the square.
Okay, so how many ways are there? To color the vertices of a square with 2 colors.
So when you say 2 colours, every corner has to be coloured in.
Yeah.
Okay.
So every vertex is black or white.
Mhm.
I'd say red or blue, but the book says black or white. So surely there are 2 options for every vertex, and there are 4 vertices. So must be 16 ways to color it.
Have you put a H in there?
Yes.
Oh no.
But yeah, because of the rotations, it's the same.
But that means that, for example, that's one way. And that's another way. So this one is different. Because in this, we have vertices 1, 2, 3, 4. 1, 2, 3, 4. Okay. So on the left, 1 is black, right, 1 is white. So they're different ways of coloring the square. But that's not what we really want to know, because what we really want to know is how many different ways are there such that you can actually distinguish them when you look at all the symmetry where rigid motions, if you like. No, not rigid motions, but the really symmetries. Okay. But these are not really different. Okay, so in fact, what so in fact, what we're after is there are 4 white, there's 1 black, there's 2 black. There are 2 different ways, adjacent black and opposite black. And there's 3 black. They're all the same.
Oh yeah.
And then there's 4 black. That's it. So it's 1, 2, 3, 4, 5, 6. Okay.
I still thought as this wasn't the challenge.
This is simple to count. However, what we want to do is count it using the orbit counting lemma. So what are we actually counting? Okay, so what we have is, so this set X. I'll call it X tilde in line with the book. Is we're looking at all colorings, C. So C is 1, 2, 3, 4, going to black and white. Okay, so we're looking at all maps that map vertices of the square to black and white. It's a coloring. And we've got the dihedral group because so the dihedral group, which is the group of symmetries of the square, that gives us all the things. So for example, this, you rotate this square, and this coloring, you get this coloring. Yeah. So the rotation is, you can see there's a permutation of the vertices. So here you would have, that would be the permutation 1, 2, 3, 4. C1, so this is coloring 1, and this is coloring 2, to C2, C, C. Do you agree? Yeah.
Maybe different.
Right, what different?
Do it, never see one, see
Well, that's the point. But C1 is a map that maps 1 to black, 2 to white, 3 to white, and 4 to white. C2 is a map that maps 1 to white, and 2 to black, and 3 to white. But so they're not the same because they are completely different. Different values in 1, and they have different values in 2. But they're different maps. And that's exactly what we're saying, is that they're actually the same because there is an element of this group that moves that to that. But we haven't quite defined the action, but the action is, I have, so in what I've done after acting is I look at, so I want to know what color of 1 is, I have to look at what came to 1, that was 4, and I look at what 4 was colored in C1. So if I have an element of this group, so that's a permutation. And I want to know where, so C sigma 1, sigma C1 is C2 in the action. Now, what do I, so C2, so I think I need C2 composed with sigma. Should be C1 or something like that. Is that right, or am I writing it the wrong way around? C1 said 1 is black. But that's the same as saying 1 moved to 2, and I check 2 in C2. So first move 1 to 2, and then I check what C2 says. Okay?
Is it?
Is it?
C1 is.
Well, you can define it either way because it doesn't matter. You get the same number of orbits in both actions. But the way I said it is, I have this coloring, and then I rotate the square, and I want this coloring. I'm looking at is, okay, so for example, what is C1 of 1? So C1 of 1 is supposed to be, I look at sigma of 1, which is 2, and I look at what C2 does to 2, and that's black, so I'm getting black. So it seems to be correct. I mean, it has to be either this, or it has to be sigma inverse, yeah, and I think this is correct because of what I've just said. No, persuaded myself, so. Okay? So we all I'm defining the action on this X tilde by saying if I take viewing an element of this as a permutation, which is what we really did, then what it does to a coloring is it sends it to a coloring that satisfies this, which is the same thing as right. C2 is C1 plus with sigma. This is nothing.
It's like an ice cream cone.
Yeah.
No
This
ice
is
cream.
a symbol saying no ice cream C2 equals C1. Okay.
What's it? Ice cream. That's my favorite mathematical.
Again. No.
So now the group D4 consists of the following elements. The identity. Then we have a rotation, which is 1, 2, so that's R. Rotation, 1, 2, 3, 4. Then R squared. I think it's 1, 3, 2, 4. Yeah. R3 must be the other 4 cycles, so 1, 3. Yeah, 1. What? 1, 4, 3, 2. And then we have RS, which I don't know what it is.
When you sat there on the opposite side, writing every single one down.
Well, that's the wrong group. You could also put your hands to the facial symmetries like.
What am I doing? I can't do that.
Shouldn't we be doing the symmetries first, yeah, and then composing them with the rotations.
So symmetry is 1 goes to 2, 3 goes to 4. So now if I compose this, so I do 1 goes to 2, goes to 3. So that's not good. Oh, 3 goes to 4, goes to 1. I'm getting this again.
Okay, you're not. One goes to. Yeah, there's
No,
no
no.
be disjoint.
2 goes to 1, goes to 2.
Rotation
Okay, yeah,
square
so
should be
it's two,
disjoint.
2 stays and 4 stays. It works. So R squared S is 1 goes to 2, goes to 4. 4 goes to 3, goes to 1. Yes. 2 goes to 1, goes to 3, yeah. And then this one is
1 closed, 2 goes to 1 and 1 goes, and then 1 goes to 3. 1 closed up and then
so 1 goes to 2, goes to 1. 2 goes to 1, goes to 4. 4 goes to 3, goes to 2. 3.
That's for the opposite. Yeah.
I was
Okay,
yeah,
so-
yeah.
how many fixed points?
First one's 4, second one.
Rotations for.
So the identity fixes everything.
Yeah.
That's 16. Oh yeah, because we're acting on the colorings now. Look.
God's sake, what?
Not on the vertices. On the vertices, I can tell you how many orbits because anything can go anywhere by rotating it. What we're trying to count is the orbit and the coloring. Okay, so this fixes everything. Every coloring stays.
So that's why we get 16.
And we get 16. The rotation by 1. That. What does that? Okay, so what can that fix?
None of it. Just keep rotating.
That would seem to be the case. However, if you color everything white, then that's fixed by the rotation. Yeah?
Yeah.
So everything white or everything black is fixed by the rotation by 90 degrees. So that's 2 fixed points. Rotation by 2, that means that these 2 vertices have to have the same color. And these 2 vertices have to have the same color. That one goes there and that one goes there. Right?
Yeah.
When you look at this, 1 goes to 3, goes to 4.
Yeah.
So they can have one color, they can have another color. That's 4 different coloring.
Yeah.
Why?
Yeah.
2. What's the other one?
That's 2.
And then. Oh, yeah, they stage one.
We step out.
So, so you pick one color for the vertices 1 and 3, black or white,
I got
and
that.
another color for the vertices 2 or 4, black or white. So 2 options here, 2 options here,
Yeah.
4 altogether. In fact, that's starting to look like a theorem. Okay, let's have a look at this. Two choices for 1 and 2. They have to be the same because 1 goes to 2. So if coloring is fixed by this permutation, then 1 and 2 have to have the same color. And 3 and 4 have to have the same color, but it can be a different one today. So again, we have 4.
2, 4.
Yeah, it's 8. Right? Because 2 stays put, so it can have any color it wants. 4 stays put, so it can have any color it wants. And 1 and 3 have to have the same color. So you have 2 options there, 2 options there, 2 options there.
Eight, yeah.
Yeah.
8, 4, 8.
Right.
On average,
24,
Why is that?
24, 48.
Because there's two options for one. There's two for each one. There's two options for what the vertex labels want. There's two options. There's 2 and 4 from the 10. And then
3,
two options.
yeah. 3.
So 2 and 5 are the same.
Yeah.
Which means that 2 and 4 together are
it's 48. Divided by
Oh.
8.
so
6.
1.
Sorry.
3 would be surprising because we know we would have it.
There's 2 times 2 times 2. It basically each bracket is a choice in itself.
We already got algebra for this. Why are we
And Laura, think of it as 1 and 3 have to be black, and then 2.
Equation.
1 and 3 can be black, 2 can be black, and 4 can be black. Then it could be 1 and 3 are black, 2 can be black, then 4 can be white. Then 1 and 3 can be
Yeah.
black,
It's
2
not good. I get it. Sure. Whatever. I believe you.
I believe
I
you.
believe you.
I believe you, then.
Every time someone says I
So
believe you.
each of the brackets is one colour. Okay? But they can be the same or different between brackets. They're different. Okay, so when we do the average,
The identity is actually 4 brackets as well. Because it's each one within itself.
that's true.
Yeah,
So it's 2 times 2 times 2 times 2.
yeah. I think there must be a theorem in there that the bigger the bracket, the smaller the number. Because look, 1, 2, 3, 4 is 2. And then when there's 2 brackets, there's 4. Then when there's 3 brackets, there's 8. And then when there's a singular bracket, there's 16. But like you say, because it's 4.
There's 4 choices,
Yeah, because essentially
this, in
each
fact-
bracket times 2.
Wow.
Each bracket times 2. That's all it is. There you go.
This is in fact 4 1 cycles.
Yeah,
When you
4
want to.
times, well, 2 to the power of 4, basically. So yeah, it's
That's what I'm
48, not 24, Jordan. Can't even do basic maths now.
Okay, so we've calculated that the average number of fixed points is 6, which is indeed the number of orbits that we did by hand there. And the thing that we've been observing doing this is a proposition.
John, I forgot to write down all of this.
I don't know anything. I don't look down my own words.
I don't know how you can write
Can't
anything.
write and stand at the same time.
It helps me.
I just don't miss it.
So you have to pick one position. Ooh. Do you have to go to another lecture now?
Yeah.
So I can write the proposition. Okay, because I've slightly rephased it from the book, but it's the same thing. Just let G be a group of permutations.
PPG.
So yeah, the other day I was trying to think about word association, and the G part was for gangsters, and then the H was homies. So like for all the homies in the gang.
Or the finite set X.
I was so proud of myself. And now I can't get it out of my head.
Well, actually, this is sometimes called y to the x for some set y. So you've got a set x, okay, and you look at all possible colorings with values from y, just like we were doing. And let G act on this x tilde by, so if you take sigma in G and look at what it does to, oh no, not X, C, sorry. Look at what it does to a coloring C, is it does C after sigma, or you can take sigma inverse, doesn't matter. Don't read it sigma inverse, but whichever way you write it. Not really. Doesn't make any difference. So if n is the number of cycles in the cycle decomposition. So the cycle decomposition means it's into disjoint cycles like we have in the example above. The cycle decomposition of some sigma in the group. Then the number of fixed points on the X tilde from the sigma is, what is it? It's the same idea as we had before. It's already 52 minutes in or something. True, because it's in the frame. Okay, so what we had was each of the cycles gets one color, and between cycles they can get same or different colors. Okay, that was the idea there. So the number of colors you can pick for each of the cycles is the size of y, because y is the colors, and there are n to choose from. Okay. So the proof is kind of clear. Proof C book. But the idea is, so the ones that are in the same cycle, these elements have to be colored the same color, and these elements are the same color. But between cycles, they're independent. So for each cycle, for each of the brackets, you get to choose among this many. And so this is size of y, this is size of y, this is size of y, so altogether it's size of y to the number of cycles. Exercise. Check
There's no examples here. Okay.
that. Yeah, n is.
That makes sense. It makes sense.
All right. Okay.
Check that. There are 55 ways to full color the square.
Okay.
Goodbye.